Now coming to the packing fraction or the packing efficiency. Alright, write it down. What is packing efficiency or packing fraction? The percentage of the total space filled by the particles is called packing efficiency. The percentage of the total space filled by the particles is called packing efficiency. Particles means atoms, molecules or ions. Suppose if you are having a lattice structure, so how much space is being occupied by the atoms or the molecules or the ions? Alright, which is expressed in percentage, that how much? Let us say 70%, 30%, 40%. So that is known as packing efficiency. So the remaining what it will be? Suppose 70% space is occupied, then what will be the remaining? Voids, empty spaces. Because 70% space is occupied by the atoms or the molecules or the ions. So remaining 30% is your voids. Voids means what? Empty space or vacant space. Remember it, voids, V-O-I-D-S, voids means vacant space or the empty space, we can say that. Clear? That's said to be yes. Okay. Or we can say the fraction of the total space filled by the atoms or by the particles or the molecules or the ions is called as packing fraction. The fraction of the total space filled means that is, suppose total space, let us say the solid is cubical. Okay, the solid is cubical and the side of the cube is A, the edge of the cube. So what is the volume of the cube? A cube. So out of A cube, how much percent is being filled by the atom? Because that is the total space available to you. Alright, or in terms of fraction, how much fraction of the space is being occupied by the atoms, molecules or ions? That is called as packing fraction. I hope you got it. What is packing fraction? Now, based upon the type of solid or the type of lattice, already we have read it. We are having SCC, simple cubic cell. We are having BCC, body centered cubic. We are having FCC, face centered cubic. I said you already that one is obsolete, that is ECC, end centered cubic is obsolete. We no more use this particular one, we can say that. Clear? You know it already. So, first we are going to start from simple cubic, that is SCC. From there we are going to start first. Let us see what is the packing fraction or the packing efficiency. Remember it, first we always find the fraction, then you multiply into 100%, that will give you efficiency. Very simple. First you will always calculate in terms of fraction. Then when you multiply into 100, that you get the efficiency. That's known as packing efficiency. So now suppose in case of SCC, look here the diagram. So what we find is that SCC comes under the primitive cells and BCC, FCC comes under the non-primitive cells. We can say that. What is the difference between that? You have seen in the AV. In case of primitive cells, the atoms at the corners touch each other. The atoms at the corners, they touch each other. See here, they are touching each other. The atoms at the corners, they touch each other. Here you can see. The atoms, they are touching each other at the corners. Let us say the four corners are there. These are four corners. The atoms at the corners, you can see very clearly it is touching each other. So this space which you can see here, what is this? Voids or empty space. This one is the voids or empty space. Alright, now what is the voids or empty space in this way? So now we are going to find that in a particular cubical solid, how much percent of the space is occupied by SCC. If the atoms are arranged in SCC, in simple cubic cell, then how much percent space is being occupied by the atoms, molecules and ions, and the remaining from 100% if you subtract, you will get the voids, the empty spaces. I hope you understood. So in case of SCC, that is simple cubic cell, and again I repeat, it is a primitive cell. The atoms at the corners, they are touching each other. You can see the atoms at the corner. Let us say this is the center of the unit cell. See, they are touching each other. Now this, the radius of the atom is R. Alright, radius of the atom, and this is center of one unit cell, this center of another unit cell. So as you can see, I am drawing a unit cell, a particular unit cell, I got it. Now this is your A. A is the edge of the unit cell. This is A, this is A, this is A, this is, because this is nothing but a what is that? Square. In terms of 2 dimension, I can say it is square. And when I arrange in a 3 dimension, the square only becomes a cube. Alright, lengthwise, breadthwise, heightwise, when we expand it, then it becomes a cube, you know it. So here I can say A is equal to 2R, isn't it? This A and this is your 2R. This is the radius of the atom, which is nothing but A is equal to 2R. Let's alright, now first is your volume of the unit cell. This one. This is a unit cell, volume of the unit cell. So what is the volume of the unit cell? It is A cube A is your 2r, so 2r whole cube. So it is nothing but 8r cube. We got it. Now, number of atoms per unit cell. Number of atoms per unit cell is nothing but is your Z. That is Z. How much it is? 1. We have seen it. How it is 1? 1 by 8 into 8. There are 8 corners are there. So what is the contribution to each corner? 1 by 8. 1 by 8 into number of corners. How much you got it? 1. So number of atoms per unit cell in case of SCC, mind it, SCC, simple cubic, is what? 1. So here you can see 4 atoms. Similarly, 4 more corners are there. This is 4 corners you can see. Contribution to each corner is how much? 1 by 8. Here 4 atoms are there. Similarly, 4 more atoms are there. Alright, so each atom the contribution will be 1 by 8. Alright, so in this way. Now, what is the volume of, that is each atom? This atom, volume of each atom. Now, atom is spherical. So, what is the volume? 4 by 3 pi r cube. We can say that the volume is 4 by 3 pi r cube. Clear? 4 by 3 pi r cube, you know it? Let me write this one little bit here, otherwise you will get confused later on. A is equal to 2i. Fine. Now, next is, what is the total volume of atoms in the unit cell? 4 by 3 pi r cube into 1, because number of unit cell is 1. Number of atoms in unit cell is 1. So, total volume of atoms occupied, what you can say, by the atom per unit cell is 4 by 3 pi r cube into 1 into number of unit cells, that is 4 by 3 pi r cube. So, packing fraction PF, we can say, is what? That is nothing but the volume of the atoms occupied. So, volume of the atoms occupied is 4 by 3 pi r cube. And a total volume, mind it, total volume. I hope you understood. After that, I write a sentence. I am not writing it here. You understand it. Total volume of atoms, what you can say, per unit cell. In case of SCC, how much it will be? 4 by 3 pi r cube into number of atoms per unit cell. Number of atoms is 1. So, you got 4 by 3 pi r cube. Divided by, packing fraction is total volume of atoms per unit cell divided by the volume of the unit cell. Volume of the unit cell is how much? 8r cube into 100%. If I convert it into, now if I keep this much, only this much, then what I get? Packing fraction I get it. You cancel it. 4, 2, so pi by 6. So packing fraction is pi by 6. Now if I want to convert into packing efficiency, what I need to do? Into 100%. I'll do it. Into 100%. So how much it will come? You calculate and see, it comes to be as 52.4%. So that means 52.4% of the space is occupied by the atoms, and the remaining is voids or empty spaces. So this is 52.4%. So packing efficiency is 52.4%. We can say. Clear? So this is for SCC. Similarly, we will calculate for FCC. Now FCC, it comes under non-primitive unit cell. In non-primitive unit cell, the atoms at the corners, they do not touch each other. That's the most important thing. You have to understand it while drawing the diagram. The atoms at the corners, they do not touch each other. They are not touching each other. See, these are the atoms at the corners. Clear? Are they touching each other? No. The atoms at the corner do not touch each other. Let me draw this one a little bit better. Okay, fine. Now, in FCC, the atoms here at the center of each face. This is one face. Alright. This is one particular face. We can say that. Clear? So, this is a center, this center, this center, and this is a center. We can say. So, atoms, this is at the center. You can see I have done it here. Dotted line, you can see the atoms at the center. So, I have to find here, same thing, packing efficiency, I have to find out. So, what will I do? I will just join this particular centers. I will join it. Alright, I will join this diagonal. Let me name this as a triangle ABC. Alright, now, you know, this is R, this is also R, this is also same atom. The volume of the atom is same thing here. That is, radius of the atom is same thing here, R. So this one again it is R, and this one is again it is R. Okay, of course it does not look like same, but you consider it that it's same, because I am poor in drawing. I am not so good in drawing, so to say. So I can make little bit better this one. Yeah, little bit better I can make it. Fine. Yeah, this one. So whatever it is, you can see here this one. That is, this one is R, R, R. So hence what you get it here, that AC here it is come to be at 4R. And here AB is your nothing but A, the edge of the unit cell, and BC is also your A, the edge of the unit cell. Alright, edge of the unit cell is what? I have already said you, that is A. Here the atoms at the corner, they are not touching each other, mind it. So here in triangle ABC, which is a right angle triangle, you know that AC is equal to root over of AB square plus BC square. You know it, this one in maths you have studied, Pythagoras theorem. So it is A square plus A square is equal to nothing but root 2 A square. Alright, fine. AC is equal to AB square plus BC square, a whole root over. So we got it. Now here what we get it is that is root 2A square, or I can write this one as 2A square. So that is nothing but A root 2. I can write it, no problem. Fine. Now AC is 4R. I have written it there, you can see 4R is equal to A root 2. So A is equal to 4R by root 2. Why did I find A? Because I have to find the volume of the cube. Volume of the unit cell, that is volume of the cube. So I already said volume of the unit cell is what? It is cubical. And what is the volume of the cube? It is A cube. So I need to find the value of A. So A it is here nothing but, we got it this. Fine. So hence we got it, A cube is nothing but your 4R by root 2 whole cube. 4R by root 2 whole cube. Now one more thing, listen here. That is, in case of SCC, you got it, SCC, A is equal to 2R, you got it. So fine, they may also ask you R. R is equal to what? A by 2. R is what? Radius. And if it is diameter, diameter is equal to 2R is equal to nothing but A. Mind it, this is for SCC, this one it is. Then in the numericals you will see this will be used. R will be used, diameter will be used. Diameter in the numericals, in case of ionic compounds, it will be the inter-ionic distances. The word will be there. Inter-ionic distances. Listen carefully in the numericals. For in case of ionic compound, in case of ionic solid, alright, because these atoms will be the oppositely charged ions. Let us say sodium ions, chloride ions. It will be oppositely charged ions. So there they will be asking you, that is the inter-ionic distance, means the distance of the two ions. What it will be? It is nothing but is your diameter, that particular one is. So inter-ionic distance is nothing but is your D, and D will be how much? It is 2R, which is nothing but is equal to A. In case of SCC, if it is SCC, mind it, if it is SCC, then it will be D is equal to 2R is equal to A. I am saying you, if it is SCC, repeatedly I am saying you. Alright, now if it is not SCC, let us say if it is FCC. In SCC you understood how to calculate R and D. Similarly, in case of FCC, how will you get, that is R from here? Now 4R is equal to A root 2. So R is equal to what? R is nothing but A root 2 by 4. 4R is equal to A root 2. So R will be A root 2 by 4. And what is D? D is equal to 2R. 2 into 4 root A root 2 by 4 will be 2 into A root 2 by 4. So 2 and 4 will get cancelled. So A root 2 by 2 will be. That is nothing but D. Clear? Are you getting what I am saying? So this will be definitely, you will see it is being used. Alright, now here we got it 4R by root 2. So you this one, if you simplified 4 4 is 16, 4 is 64, R cube by 2 root 2. We got it. Clear? Now I have to rub it a little bit. I need to rub. So here I am doing it. So here, that is number of atoms per unit cell is how much? In case of FCC, number of atoms per unit cell is nothing but 4. How it is 4? 1 by 8 into 8, alright, plus half into 6. Number of atoms at the corner is what? 1 by 8 into 8, plus how many faces are there? 6 faces. Contribution to each face is what? Half. So half into 6 is 3. 3 plus 1 it is 4. Got it? So hence it is coming to be as 4. I hope you understood. I have told in the previous AV also, you know that. So now next is total volume of atoms. Total volume of atoms per unit cell. So 4 into 4 by 3, 4 into 4 by 3 pi R cube. So packing fraction will be, that is nothing but 16 by 3 pi R cube. That is total volume of atoms divided by volume of the unit cell. Volume of the unit cell is how much? A cube. A cube is how much you got it? 64 r cube by 2 root 2. So here it will be 2 root 2. Clear? Understood? 16 4 5 16 pi r cube by root 3. 16 pi r cube by 3. I got it here. Now by total volume is 64 r cube by 2 root 2. So 2 root 2 goes up. R cube cancel. Here 16 4 is 64. It gets cancelled. If you multiply this, you convert into packing efficiency to 100%. You do it. You will get it to be as nothing but 74% is the packing efficiency, which is the maximum, we can say that. So FCC is the most efficient type of packing because here 74% of the space is occupied by the atoms. One more is left, BCC is left. Alright, but it will be less, you will see that, than FCC. So it's the most efficient packing it is considered. Means the atoms are most, more tightly packed in case of FCC, then BCC, then SCC. Of course, BCC I have not found it out, and I'll find it out. I'll say you in the same way we'll do. Alright, and remaining that is 26% is your nothing but voids, we can say. I hope you understood how to find the packing fraction SCC and FCC. We'll come to BCC next.